So first, I'm going to cover, as I said, some of the major topics of this course and the themes for this course. And so the basic idea is, let me put this on normal. I think it's already on normal. Okay. Why is physics interesting to study? Okay. Or why should we study physics in a liberal arts school? I know I went to a liberal arts college and I benefited tremendously, although I'm a physics major, I benefited tremendously from humanities courses because I learned a lot about what our culture is all about, the Western culture, let's say, okay? And in particular, if you study science or study physics, you realize, if you take any of the physics courses, that our culture values science for its stream of inventions which improve our lives, okay? So let me just kind of throw out and invite you to just shout out some examples of inventions that have improved our lives that science is responsible for. You use it all the time. Light bulbs, very good, okay. Something more modern. Computers, very good. Cell phones, cars, refrigerators, etc., etc. So there's lots of examples, okay? CD players. However, I'm not interested in any of those, okay? This course is not about how these things work or what's the physics behind inventions and about how these inventions have benefited our culture and our lives, okay? What this course is about is that science is not only important to us for these technological consequences that we talk about, but about the intellectual satisfaction that science gives us, okay? So that, for example, when you read a poem, apparently you get some satisfaction, some intellectual satisfaction. Well, what I'm going to try to shoot for is to give you the similar degree of satisfaction when you understand about some of the scientific endeavors, as if you were to read a poem, okay? So that's what I'm going to try to do, but I'll make it more concrete than that, okay? And the goal is that since science opens up our understanding and gives us a new horizon about what the world is about, satisfies our curiosity, and it opens up our imagination, okay? These are the things that will provide intellectual satisfaction. So some of the subjects that all civilizations have been occupied with, and we're still occupied with, is, what is the universe? The universe is immense. What are stars? What is sun? What are planets? What is our Earth? What is the role of these astronomical objects in the universe? Okay, galaxies like our Milky Way, etc. And these lead to deep questions, such as, what is our world made of? Okay. Now, I'm not really talking in trivial terms. I really want to get down to some of the fundamental constituents of the world. Okay, when I say the world, I mean it in the most general sense. So I could apply to what are stars made of? Are stars made of the same thing as we see on Earth, or are stars made of different stuff? Okay, and where did the Earth, Moon, and the stars come from? Okay, so we'll get to that. The evolution of the universe, the evolution of our solar system. Okay. What is the composition of all the matter in the universe? Okay, do we know about it? And as you will see, the answer is we don't. Okay, that there's a lot of stuff out there that we still don't know what it is. Okay, we have even invented a name for it. We call it dark matter. Okay, because we don't know what it is. All right, but literally, there's a lot of stuff out there that we don't know. We know it exists, but we don't know what it is. Okay, so we'll talk about what we know, of course, and then we'll talk about what we don't know too. Okay. All right, and then these kind of questions and these kind of efforts into understanding will, of course, lead to further questions, which will give food for thought. All right, so we will, of course, ask the questions about the origin of the universe, the origin of the solar system, and so on. But we'll ask deeper questions, like, what is space, time, matter? Are there any connections between these entities that we are so familiar with? Okay, and that's really what physics is all about today. And we are all very used to thinking about space in 3 dimensions. People who've studied math, you've studied X, Y, Z as the 3 dimensions of space. And is space really just these 3 dimensions, or are there more dimensions to space? Okay, turns out that the latest physical theories require that there must be more dimensions in space. And the latest experiments that are set out to discover new things, one of the things that the latest experiments are set out to discover is extra dimensions in space. Okay, so we'll talk about that. Not right away. Or are there parallel universes? Or do we live in a unique universe? We'll talk about that. Okay. Now, again, I don't want to talk about all of these things in the esoteric sense all the time. I want to give you a grounding, a foundation in what we know that you can solidly base these new ideas on. Okay. So, or are there other worlds like our own, etc. So I'm sure you can think of similar questions in this nature. Okay. All right. So the point, again, coming back to the goals of this course, is that when we expand our thinking to the universe and our place in it, we begin to wonder some of the basic questions, namely, can we really understand the workings of the universe? And the answer, of course, is yes. Okay. And now we come back to some of the more basic questions that were that humanity was involved in before the success of science. Is that, are there natural laws that explain nature, or is nature completely determined by divine command? Okay. So certainly we know how nature behaves. We can understand how nature behaves. But what I'm trying to address here is, can we hope to fathom the laws of nature, not only the ones that we already understand, but can we understand further what nature is about? Okay, that is what we are calling scientific thought. That's what this course is about. Okay. All right. So I'm going to try now to become more focused about the plan of how I'm going to address these many different topics, which are in themselves rather vast in my undertaking. Okay. So the way I'm going to do that is I'm going to explore the first area of science which emerged to show that indeed the universe has order, has a design. Okay? There's a design to the universe. Okay? And that there are natural laws, okay, that govern phenomena in nature. Okay? Now this is not just a view that evolved in science. What's interesting is that as science came to this view and success, people in other fields thought of the same thing. Okay, so for example, Shakespeare, who I'm sure you're all very familiar with, stalwart of literature, he writes in this famous play, Troilus and Cressida, the heavens themselves, the planets, and this center. What do you think it is referring to by this center? He's actually thinking about the Earth. Okay, this center. Observe degree, priority, and place. Insisture, course, proportion, season, form. It's interesting. He calls proportion. Okay, he'll talk about proportion or mathematical laws in this course, in section, etc. Season, form, office, and custom in all line of order. Okay, so by the way, he coined this word insisture. Okay, and I looked it up in the dictionary, and it means natural place in order. So it's the same thing as the other the other parts of the poem. But the point is that Shakespeare, being a thinker of the Renaissance, or a little bit beyond the Renaissance, was already thinking in free scientific terms that the nature can be understood. It has a design. Okay, it has order. Okay, so that the basic idea is that the universe is fundamentally orderly, and that there are natural laws. Okay, and this is what you might call a triumph of science. Okay. So what I'm going to try to do is I'm going to talk about the first such triumph in science that really figured out the laws. Okay? And this was the guy who made that first great success. Okay? There were others before him, but he made the first great success. Who's he? Isaac Newton, very good, and recognize him because of the apple. Right, okay. So we'll talk about that, of course. But here I want to just emphasize that his triumph was the first triumph, and we call it Newtonian mechanics, and that's really what I'm going to be focusing on a lot. And the point is that he penetrated the laws of motion in the universe. Okay? So we're going to try to show you how he figured out the laws of motion in the universe. And when I say that, I mean the laws of motion on Earth and the motion in the heavens. So which means the laws that govern how things fall, or how things, move if I throw them at an angle like that. how things move. So the laws of motion on Earth, okay, and the laws of motion in the heavens, okay. So other motion phenomena on the Earth, for example, is tides or waterfalls and so on. But then motion phenomena in the heavens is the motion of the moon going around the Earth, or the motion of the Earth going around the sun, etc. Okay, so he figured out the laws of all of these objects moving around the Earth and moving around the sun. But what is more important is that he figured out a uniform set of laws, and I'll come back to that in a second. Now, I want to emphasize that his success was really a grand success, because before him, right, before Newton, people always thought that heaven and earth, in the sense of astronomy and what goes on Earth, are quite different. In other words, there are different laws that govern the motion of the planets and different laws that govern the motion of objects on Earth. Okay? So before Newton, it was generally thought that these are different regions. And in fact, not only the science, but also our art and literature reflect this belief. Okay? And the great example of that is, in fact, the Bible. Okay? God separated heaven and earth at creation. Okay? So there's this famous picture of God creating the universe, okay, separating heaven and earth, and a nice statement at the beginning of the Bible that says, "And God said, let there be a firmament in the midst of the waters, and let it divide the waters from the waters. And God made that firmament and divided the waters which were under the firmament from the waters that were above the firmament." So basically, he divides heaven and earth into different regions. Okay, I'm putting this out there for you to impress upon you that not just preachers and not just religious people believe that heaven and earth are different regions, but so did scientists. Okay, and what Newton did was he synthesized the two regions. Okay, so he used the same laws of motion to understand astronomy, which is what is the physics of motion in the heavens, and dynamics, which is the physics of motion on Earth, let's say. Okay, and the point is that he successfully explained, and in quantitative detail, which you will appreciate by the end of this course, okay, what the quantitative detail was. Okay, and he explained the motion of the heavenly bodies, the sun, the moon, the planets, the comets, the stars, etc. But what was the most wonderful thing about Newton's triumph was that he used one set of laws, okay, one set of laws to explain motion on Earth, and that same set of laws to explain the motion in the heavens, which means he unified heaven and earth. Okay? So that was really his great accomplishment. And in fact, as I will come back, we're always trying to unify different areas of physics. Okay? We try to unify light with electricity and magnetism and so on. So we'll talk about that. So Newton's accomplishment is nicely captured by this poem by Alexander Pope, who says, "Nature and nature's laws lay hid in the night, and God said, let Newton be, and all was light." Okay? And there's another poem, a poet, William Blake, and poet of the Enlightenment, who's actually an artist too, and he kind of shows Newton naked and alone, using the power of mathematics to figure out God's design of the universe. Okay? That's what we're going to try to make you appreciate in this course. Okay? Now, what's also interesting, and you might branch out into this, Newton's success actually generated tremendous optimism in our culture. Okay? Something that had not been experienced before, because here was an example of a success in showing that there is a design in the universe, there is an order in the universe, and there are laws that govern nature, and that in fact, in this case, he figured out the same laws operate on Earth, operate in the heavens, okay, and operate everywhere in the universe. And his success, in fact, forged a very strong confidence in the power of human reason, that we can figure these things out, okay? That the human mind is capable of discovering these laws, which of course has its impact in other fields, like in economics or market theory or whatever, business and so on. You're trying to figure out how things work because you have the confidence that you can understand the underlying laws by thinking about them in a rational sort of way. In fact, Newton's mechanics and his approach became what we call the prototype method of scientific inquiry, okay? The model that scientists emulated throughout the developments of science. And since that time, science grew to become one of the principal activities of our society, okay? So we see, in fact, that the National Science Foundation and the Department of Energy and NASA and all provide lots and lots of money to give to the advancement of science, because they have an ulterior motive, of course, that maybe science will come up with some great inventions that will help society, or maybe they'll come up with some great weapons that will make us a powerful country, etc., etc. But the point is that science became an important quest, in our culture, okay? It became a higher quest. And science became a higher quest, even higher than what Newton figured out. And a nice way to express this lofty nature of the scientific quest comes from another famous person that I'm sure you recognize. That's Einstein. And he says, in my efforts in trying to figure out physics, okay, I want to know how God created this world. I am not interested in particular in this or that phenomenon. I want to know his thoughts. Okay? The rest are details. Right? So we're going to try to give you a feeling of how Einstein approached physics and what some of his discoveries were. And I'll show you that. Now, Newton, of course, was much more modest about his accomplishment than Einstein was. Einstein said, I'm going to try to figure out God's mind. Okay? Well, Newton was very modest, and there are many interesting quotes from Newton. I'm going to use this one because it's appropriate to the course. He said, I have seen further than other men. If I have seen further than other men, it is because I stood on the shoulders of giants. Okay? And I like this quote because it allows me to introduce how I'm going to develop this course. Namely, I'm going to talk first about the giants on whose shoulders Newton stood. Okay? So who were these giants? So if I look backwards from Newton, there was Galileo, who lived in the Renaissance, and Kepler, also in the Renaissance, and Tycho Brahe, who came before him. And then before them came the Greek era of Ptolemy, Hipparchus, Apollonius, and before them came Aristarchus, Archimedes, Euclid. I'm sure that you've heard some of these names before, especially, for example, Euclid, right? And we'll try to, and then, of course, before that was Aristotle, Plato, Pythagoras, and Thales. So we'll try to understand how thinking of Newton was based on the ideas and the progress of these scientists, okay, or philosophers who came before him. And that will give us a feeling of why Newton was trying to say that if I have seen further, it's because I stood on these shoulders. Okay, so here, by the way, is a nice picture of the Earth from Mars. Which I use as a background to discuss with you the threads of this course. Namely, these scientists, who were they, what did they do, how did they discover what they did? And I want you to try to appreciate Newton's accomplishments, okay, by appreciating what his predecessors did, okay? So we're really going through the entire history of scientific thought up to Newton, but we're not going to just do that, okay? We're just going to follow the main threads, okay? We're not going to do that entirely, because then that will become a history of science course, okay? The reason I'm going to do that is that I want you to appreciate and understand not only motion, not only the physics of motion in the heavens and motion on Earth, but also the basic ideas behind the progress of all scientific thought. Okay, so that's the main reason for following this. Now, I have to make an apology right now as to my approach. Okay, I am going to follow what I call the Eurocentric view. And the reason is that I'm going to end up with Newton. Okay. Now, if you, for example, go to different cultures, Egyptian merged with the Eurocentric, the European culture. But if you go to Indian culture or Chinese culture, they also had tremendous advances in science and so on. But I'm not going to follow those threads because they do not lead to the Newtonian mechanics. Okay, so please forgive me for being so Eurocentric. And you're welcome, by the way, in some papers and so on, to talk about the scientific discoveries of other cultures. So you're welcome to do that. All right. So now I've kind of thrown out many different ideas to try to give you a flavor of what I'm going to try to accomplish. Okay. So now I'm going to try to go more systematically to give you the plan of the course, okay? And it also connects to the plan of the book, okay, which you're going to read in connection with the course material. All right, so I'm going to divide this up into three segments, okay? The first segment will talk mostly about Earth and motion on Earth, okay? And so we'll start out with talking about the Greek universe. And believe it or not, the Greeks really knew or really understood that the Earth was round, the Earth was a sphere. We'll talk about that. But not only that, but they came up with the ideas about the elements of the Earth, okay, the elements of the universe, Earth, air, water, fire, ether, etc. And they came up with a cosmological organization for the universe based on these elements, okay. So we'll start with the Greek universe, okay. And I don't want to kind of leave you hanging with some of these ideas that have been outdated. So what I will do is at the end of every chapter, I will try to update you on what some of the modern thinking is on the same subjects, okay? So of course, if you're talking about the subject of the elements, we know it's not earth, water, air, fire, ether, etc. It is these, the chemical elements that how many people have seen this, right? In high school, everybody's seen the periodic table of elements, right? So these are what we call the elements. And this is called the periodic table. And turns out, by the way, that just as the Greeks, were trying to make a picture of what the universe is made of, and the picture consisted of what they saw: water, earth, fire, air, etc. We have progressed to that with this table of elements. My God, we got 100 elements in here. Okay, turns out those are not the elements anymore. Okay. The elements that that we know today make up these elements, okay? We know that there are more fundamental elements that make up these elements, okay? And these fundamental elements are these guys, okay? And they're called the quarks and the leptons, okay? So what I'm going to do is I'm going to start with some of these Greek ideas, all right? And then take you to the more modern views, which you're familiar with, and from there I'll take you to the ultra-modern view of quarks and leptons, okay? Now, I don't expect you to be able to understand all the details about quarks and leptons, but there is one connecting theme that you will see that I'll come back to. Okay, so that basically will cover chapter 1 and chapter 2, and then we'll continue with the discoveries of the thinking about motion on Earth that came from the Renaissance through Galileo and others, okay? And then finally we'll talk about how Galileo understood motion on Earth in terms of horizontal motion, like motion of the billiard balls on a table, or vertical motion, like motion of water down a waterfall, or even two-dimensional motion, which is a combination of horizontal and vertical motion, right? So if you opened a bottle of champagne during the New Year's or during Obama's inauguration or something, you could see that the cork of the bottle of champagne took a trajectory, right? And what that trajectory is, how many people know what that trajectory is called? There's a mathematical name for this trajectory. Parabola, right. So we're going to help you figure out from Galileo's understanding of motion, how you get this parabola, okay? All right, so as I said, in order to get to the parabola, you will have to understand some simple numerical aspects. And that's what we will cover in section and in the appendix. And then again, as I said, we will do updates, okay? So when we talk about motion, when we talk about Galileo's laws of motion, we'll update it with Einstein's views on motion. And they were very radical, okay? And they're the most modern views on motion. And the reason they're the most modern views on motion is that his views on motion led to the idea that space and time, as we think of it, are not the way physics perceives of space and time. In fact, we think of space as the same for everybody and time as the same for everybody, which means that if you set your clock and exactly to his clock, right, that your two clocks will read exactly the same forever and ever. And Einstein's view Einstein's theory, Einstein's discovery was that that's not true. Okay, your time will change depending on how you're moving. Okay, so if you get on a plane and move at significant speed and come back, you'll have a different time on your watch than he does. So time goes with the observer. Space and time, space also goes with the observer. So get ready to get beyond these beliefs, not beliefs, but these notions that you've learned that space and time are the same for everybody through Einstein's theory. Okay, so that's the update on motion. Okay, so that'll cover motion on Earth mostly. Then we'll go to the heavens, and as before, we'll start with classical Greek ideas about motion in the heavens and how they model the heavens in this simple way. You know, you go back to Shakespeare, you know, this center being our Earth, and then all the planets, even the sun going around the Earth, and then all the stars going around the Earth. And this was the Greek view. In fact, they developed a beautiful model to explain the motions of all these heavenly bodies based on this simple spherical model, okay? And it turned out that in the Renaissance, or before the Renaissance, this view was thrown out by this great guy, Copernicus, and this is called the Copernican Revolution, where he put the sun in the middle, and somebody here told me that Shakespeare, the center of the universe was the sun, and in fact, it turned out that the original Greek ideas were wrong, and that the Copernicus idea is the revolutionary idea, and then there are laws that govern the motion of these planets around the sun, which are called Kepler's laws, and we'll discuss how he came about these laws. And in fact, from there on, we'll discuss a new heaven, which would be the discovery of Galileo, again, coming back to the same guy who discovered the laws of motion on Earth, like the parabola of your champagne cork. He used the telescope to look at the heavenly objects like Jupiter. I'm showing you a much better picture of Jupiter than he saw. And in fact, you will get a chance to look at the universe through the most modern telescope available today. Anybody know what the name of this telescope is? Yes, right, the Hubble Space Telescope. So you'll get a chance to look at all the discoveries of the Hubble Space Telescope as part of your homework. You know, you'll go to the website called hubblespace.com or something, and then you can explore the universe on your desktop, okay? And you can discover what the latest discoveries are. Not only just planets, but galaxies and beyond, okay? The edge of the universe. So then we come back to, remember, we're following this path of our understanding about Earth, our understanding about the heavens as separate regions, and then we'll try to put it together in this idea of the rise of the unity of physics, okay? But the unity of motion came through a very tortured path, and that tortured path was an idea that to explain the motion of the planets, there must be some sort of mechanism. You know, I think it's become part of our language, you know, when we say, what is the mechanism behind evolution? Okay, or what is the mechanism behind some phenomenon that you are trying to explain? And this idea of mechanism came from this period where people thought that everything can be explained by a simple mechanical model. And the reason they thought that came from this effort to travel around the Earth, in fact, to discover the new regions of the Earth and so on. That's why I call it a new Earth. And so this effort of circumnavigating the globe required you to understand where you were in terms of the latitude and longitude on Earth. And what that required was precision in timekeeping, and we'll talk about that. And in order to keep time precisely, you develop these wonderful devices, which are wonderful mechanical devices. Now they're not, they're electronics. But before that, there were wonderful mechanical devices like this over here that kept time and helped you figure out where you were on the surface of the Earth. And then people got the idea that the universe was run by some sort of invisible mechanics, okay? And so this solar system that we talk about, namely the sun and all the planets going around the sun, the reason that they all go around the sun is because some kind of gears and wheels control the motion. There is a mechanism that runs the solar system, okay? So that's the age of the mechanical universe, okay? And from that, mechanics dominated the thinking, okay? And then came Newton to come with the idea to figure out what is the key to that mechanics, okay? And Newton figured out that the key to that mechanics is gravity. Okay, so he figured out that it's gravity that controls motion on Earth and motion in the heavens, and he came up with the laws of motion and universal gravitation to explain both. So that will give you the synthesis. Okay, and then again, after the synthesis, we'll talk about modern physics update back to Einstein again, where Einstein says, you know, this idea of gravity, the force of gravity, no, there's no such thing. There's no force of gravity. Okay, so Newton dismissed the idea of the force of gravity, and basically he came up with the idea that what happens is that space and time change in the presence of a heavy mass, and it's because of that deformation of space and time that things move. So we'll try to understand some of these modern ideas based on trying to understand the old ideas first. Okay, and then that of course leads to new consequences like black holes, dark matter, dark energy, and so on. So I'm not going to throw out these ideas, these new ideas at you without the foundation, okay, of the modern physics. And then ultimately, near the very end of the course, we will talk about how our quest to understand the nature and the origin of the elements really leads, step by step really, to an understanding of the nature and origin of the universe. So we start with this idea of the Earth and the elements of the Greeks, you know, water included, okay? And then we'll work our way to the fact backwards, okay? To the fact that Earth and other elements, Earth and air and fire are not the elements, but they have these chemical elements of the periodic table. But those elements are really coming, okay, instead of the chemical elements, those elements are really coming from the atoms, which has a nucleus, and that's coming from, that has protons and electrons, all of these things you've heard of, right? And these protons are made up of quarks, okay, and the electrons are a more general family called the leptons. But what's going on is that as you go deeper and deeper into the structure of matter, you're going backwards in time to the beginning of the universe, okay, to the creation of the universe at the Big Bang. Okay, so the universe started over here in the Big Bang and then expanded to the present time, okay, but our search of going down deeper and deeper is really taking us back further and further in time, okay. So that's the connection between the origin of the universe and the whole idea of elements. And so we'll try to go to that. Okay. All right, that covers pretty much the topics that I'm going to do. Now I'll talk a little bit about the style in which I'm going to cover these topics, okay? So as I mentioned when you came into the room, that I'll be doing some experiments. And one of my topics that connects to the whole course is gravity, okay? And I'm going to discuss how the views of gravity evolved all the way from the Greek times. You know, the person who coined the word gravity was a Greek philosopher. His name was Aristotle. Okay, I'm sure you've heard of Aristotle. He invented the idea of gravity through the word gravitas. Okay, and we will talk about the evolution of the idea of gravity all the way from Aristotle to Galileo and Newton and Einstein. And then we'll try to do some experiments. Now, I like this picture. But I like this work of art. Has anybody seen this work of art before? What is it called? Yes, very good. It's Rene Magritte, and it's called the Castle in the Pyrenees or something. And the reason I like it is because here's this artist, all right, who's thinking about the universe, okay? And what is his thinking doing relative to gravity? He's defying gravity, right? He's saying there's this huge rock with a castle on top, and it's just floating above the ocean, okay? So I'm going to now defy gravity for you in front of your very eyes, all right? With this wonderful experiment in physics. If you've seen this before, don't let the cat out of the bag, okay? All right. So I'm going to take this bucket and fill it with water and turn it upside down over my head, okay? And I will not get wet. So I will defy gravity. I will let that water stay in the bucket, all right? Okay. So just to prove to that, I'm going to have this transparent jug here. I'm going to add the water here. All right. And do you think I should put my coat on? You have faith? I won't put my coat on. Does anybody want to stand next to me while I turn this thing upside down over my head? Do you guys want to go in the back? See, trust me, they're not going to get wet. Okay. So we'll actually study the physics behind what I'm going to do, okay? But basically, I'm going to do this. All right? So it was over my head for a second, for a brief instant of time, right? For a brief instant of time, it was right over my head, right? Yeah, follow that bucket and see that it's really upside down over my head, okay? Right? The water didn't fall out, okay? So there you have the water defying gravity, okay? So it's a nice trick to use in a birthday party. I didn't let the water disappear either. The water's in there. And there's something very fundamental going on in there that's really connected to Einstein's idea that there is no such thing as a force of gravity. It's just motion, okay? And for those people who have read more, it's the equivalence principle. What I was doing was I was doing acceleration. And what Einstein did was he proved that gravity and acceleration are the same thing. Okay, so that's what I did. I replaced gravity with acceleration. But you'll learn that later, okay? So this picture here, by the way, can actually happen. And we'll do this. It'll actually be one of your homework problems. Maybe it'll be a problem in the quiz that says that if the Earth were rotating fast enough, you could actually have that situation, okay? A rock would actually float right on top of the Earth without falling, okay? All right, so gravity is the unifying theme throughout this course. And I like this picture, as I said, because the artist's imagination defies the gravity. And I did this experiment. Okay, so I'm going to go through very quickly now through some themes of this course. So far, I've talked about the contents, okay? Now I'm going to talk about some themes, okay? So I'm going to cover this course from a number of different perspectives, okay? One is an evolutionary perspective, which means I'm not going to just throw the laws at you or throw the science at you. Like often, if you take a physics course, you open your textbook and they say F equals ma, right? Apply it. I'm not going to do that. I'm going to show you how Newton came to the idea F equals ma, right? So it'll be more towards the end of the course that you come to F equals ma rather than the beginning of the course, okay? So it's not just the laws and the science, but cover how do we know, okay? How did the scientists discover the laws? And by that method, I want to convince you that science really is a living entity. I want to debunk the idea that, you get on the news and Katie Couric says, scientists say, therefore it's a fact, right? That's wrong, okay? Just because a scientist says so doesn't make it a fact of truth, okay? It's our thinking at present, which is supported by much evidence and theories and so on. It all sort of hangs together, and that's why we think it's this way. But it may turn out to change, okay? So science is a living entity and continues to evolve, okay? So that's one of the ideas I want to, one of the approaches I want to take, which I call the evolutionary perspective. Then I'm going to take also, at the same time, a human perspective, okay? So that I'm going to talk about these discoveries, okay, like Newton's discoveries or Galileo's discoveries, as breakthroughs and insights by fascinating people. So we are interested in the scientists also, okay? It's not just Kepler as a name. I want to talk about Kepler's life, okay? How did he come up with the idea, okay? What was the culture that he lived in that played a role, perhaps, in his thinking, okay? And then, of course, the culture leads me to this wonderful idea that it's not my idea, it's an idea that many historians of science subscribe to, which is that the theories of science develop in a certain culture, okay? And that particular culture leads not only to science, but other creative activities of humanity, like art or poetry and so on. And I'll try to make some connections between how the thinking of a particular era led to a scientific thought, and the art of that time also evolved in a similar manner. So I'll try to make the connections between art and poetry, just like I did with that painting by Rene Magritte, okay? Here's another idea that I want to pursue, that science is not only evolving, but there's a lot of creative activity going on in the development of science, okay? So these scientists are not just, figuring out the laws by rigid mathematics and logic, okay? It's not that. We basically go by the seat of our pants now and then and make some ideas up, okay? That's what I call creativity, okay? So science is a creative activity. However, even though we make things up now and then, we are always guided by some principles, okay? And these are what I call aesthetic principles. Now, what do I mean by aesthetic principles? Aesthetic principles, just to throw the words out, are that we like simple laws, we like beautiful theories, beautiful laws, we like elegant explanations, and in section tomorrow, you'll see a couple of elegant explanations of things, okay? So you understand the meaning of elegance. We like to see order in nature, okay? So whenever we have a theory, we try to put things in order. All right, and then we try to unify things, okay? So just like I showed you heaven and earth, we try to unify that. Now what do I mean by simplicity? Just to give you a better example. So nature is governed by simple laws is the basic idea, which means that suppose you have a phenomenon and you have two scientists or two philosophers sitting and trying to ponder it and say, I'm going to explain this phenomenon. And one guy comes up with an explanation that involves one idea, okay? One phenomenon, okay? One underlying mechanism, let's say. And the other guy says, well, no, there's two or three things going on here, and when they all come together, that's what happens. Well, we are attracted more to the first guy, who has the simple explanation with a single phenomenon, okay? So why? Because it's simpler. Okay, so that's an aesthetic principle which I call simplicity. So those are the kind of things that guide our free-flowing creative activity. It's not really completely free-flowing. It's guided by these principles. Okay? So if there are fewer effects and fewer assumptions, then that theory is likely to be more closer to the truth. That's what we think. So here's another guiding principle. It's an aesthetic principle. That nature has an intrinsic beauty. Okay? And of course you see the beauty in nature all the time. Okay? So when you see the palm trees and you see the butterflies and the wonderful snow crystals and so on, you say beautiful, right? And that's why the diamond is so precious, because it's so beautiful. But what is it about that beauty that we as scientists see? What beauty do we see in science? Okay? So a physical theory sees that beauty. Okay? In fact, this famous physicist called Hermann Weyl, who was also a very famous mathematician, he said, if I had different theories to think about, he says, my work always tried to unite the true with the beautiful. But when I had to choose one or the other theory, I always chose the one that was more beautiful, one that was more elegant. Okay, so what do I mean by beauty? So if you look at some of this beauty in nature, okay, you look at these patterns, okay, like the galaxy or the nautical shell or the flower, etc. There is some order in this natural objects, okay? And mathematics will help us express that order. And so I'm going to help to show you how the beauty of this beauty is underlying mathematics, the underlying order, okay? That's what I'm going to try to show you. So this will then, of course, emphasize the numerical aspects, okay? And then unity will try to show you how different areas of science are coming together. So for example, at the end of our course, we'll see how the laws of motion in heaven and earth come together. But as we go along, I will also show you how electricity and magnetism and light really come together. Okay? They're really one and the same. And that space and time are really different, not different, but are really manifestations of a combined entity called space-time. Okay? So we're all aiming towards a grand unified theory to explain all the laws of physics. We haven't come there yet. There are a lot of ideas of how to get there, but we're not there yet, and I'm going to try to give you a feel for it. All right. So all these themes will recur to the course. You look for them, recognize them, and think about them. And when it comes time to write your paper, for which there is a significant part of your grade, you write about these ideas also, if they appeal to you. Okay, I'm going to stop there for a second. Assignments of the course. You need to buy the book Unifying the Universe, and you need to buy this green book. How many people have both? Have all of that? Good. So this green book has... Okay, first of all, the Unifying the Universe book has all the companion material of what I'm going to lecture about, okay? So my lectures overlap what I say in the book, but it's not a one-to-one, okay? So I'll give you many more examples here, many different examples here. I'll skip a lot of stuff here that's in the book, but you're responsible for both.